And in that case, the amount of heat transfer from the fin can be readily calculated. We can say that the amount of heat transfer from the fin is total area of fin times heat transfer coefficient times T wall minus TA, because we know that T at every place on the fin is TW. So this is the total amount of heat that is transferred from an ideal fin. So we are calling this as ideal fin because actually there will not be TW till the, in fact, if fin is too long, the TW will be almost same as the ambient temperature, TA. Okay. So an ideal fin will have same temperature everywhere. That is infinite thermal conductivity of the fin material. And in that case, Q max is area of fin times H TW minus TA. But for an actual fin, this T at different places will be different from TW. If this is TW, this may go almost to T ambient or little less, little higher than T ambient. So that's a real fin. And because this temperature drop is reducing towards the tip of the fin, the amount of heat transfer also reduces. So the Q actual is always lesser than Q max. And we can obtain Q actual if we can get eta of the fin. So now what we'll try is that we'll analyze a single rectangular fin, the simplest kind of fin with simplest boundary condition, and obtain the expression for eta, that is the fin efficiency. And for other cases also such analysis is possible, little bit complex, we'll not do it in the class. But those are already done, and fin efficiency for different geometries are available. So we'll use those charts and tables. So today we'll learn first the simplest kind of fin. What is the expression for fin efficiency in terms of known variables? Second, for other more complicated cases, where to look for the fin efficiency data and solve problems. So this is our today's first part. We should be through by noon to this part. Any question or till this point? I have to keep close to the notation that I have in my notes. Even in my notes, the notations are not consistent in everywhere. So that's another thing I have to do. Okay. So now let us see that what we want to do. We want to obtain the heat transfer from the fin, and we'll take a simplest kind of fin. So the simplest kind of fin is like this. So it's a rectangular fin. This is a part of the surface. The surface may be very long, so this weight is long. So we are talking about one-dimensional conduction. So other dimensions may be taken as very long. So heat is transported only in this direction. So let us call it Z direction. So this is a Z direction. So we are talking about steady state one-dimensional conduction. So heat is conducted only in Z direction only. Other direction conductions are negligible. So we need to what first? Let us be clear that what we are trying to obtain. Our goal is to obtain Q actual. Q max you already know. If we can obtain Q actual, then you can place it here and we can get the expression for efficiency of the fin. And of course, the highest efficiency is 1 when Q actual is Q max. In that case, there is no temperature gradient across fin. So infinite thermal conductivity. That's not the practical case, of course. So now to analyze the one-dimensional conduction, so we'll take a differential volume. Of dz. So this much is dz. Okay. And the thickness of this fin is twice b. So here we have drawn the fin to be a little bit thicker because otherwise we cannot draw. Actually, the fins are very thin. So if I draw actual fins, so those will be very, very thin. So those will be something even thinner than this. Okay. So it's difficult to draw. So that's why I haven't drawn. So those are like blades. So those are very, very thin. So this 2b is actually very thin in compared to other dimensions. Say if we call it L, 2b is much less than L. And why it's 2b, we'll know that actually the half thickness will come and so on. So that's why you have taken on as a 2b. Otherwise, the b by 2 will come in the expression. Okay. So now we have to write the heat balance. So we can also take this as W, the width. So both W and L are much larger than this 2B. So now what you do is that you write a heat balance for this fin. So before that, you tell me that how heat is flowing in this fin. Given the base temperature is T1, that is the temperature at the base of fin is TW. Ambient temperature is TA. So first you tell me that how the heat flow occurs in this differential element. What is the heat in, what kind of heat in, what kind of heat out. So all these things.
Sir, heat comes in the fin from the Z direction and it goes out from the other direction in the X direction.
So from which direction heat comes in and which direction heat goes out?
The heat comes in from the Z direction.
Okay.
And it goes above and below. It is dissipated above, below, and to the right of the in the Z direction, where the ambient temperature is there.
Okay. Jyotiraditya Aryan. Jyotiraditya,
Yes, sir.
Please turn on your video. Okay. So heat comes from left-hand side, right? By which
Yes,
mode? What is the mode of heat transfer there?
in this one, I guess, through convection.
Through convection. Okay. Let me say. TB Tanay Gaurav. TV Tanay Gaurav.
Yes, sir.
Please turn on your video. Jyotiraditya, you can turn off your video. So heat comes from where and goes where and how? I cannot hear, you are muted. Please unmute yourself.
It flows along the Z direction and heat
By
loss.
which mode?
Sir, conduction.
Okay. So it enters the differential volume from left boundary by conduction.
Yes, sir.
It leaves the differential volume in the right boundary by conduction.
Yes, sir.
Okay. So this is what you are saying?
Yes, sir.
Okay. Okay, you can turn off your video. Let me see others. Udata, Anuradha. Varun Balkrishnan,
Yes, sir.
please turn on your video.
Yes, sir.
So heat enters in the left boundary.
Yes, sir.
It leaves in the right boundary. By which
Yes.
mode?
It enters through conduction, and on the right boundary, it leaves through convection.
In the differential volume. So tell me from which boundary it leaves by, it enters by conduction, which boundary it leaves by convection.
So
So let
through
me
Z.
mark it. So you can see this my drawing, no?
Yes, sir.
Yeah. So first let me draw this boundary. So this boundary I'm marking by red. Huh? This boundary. Heat enters by.
Conduction.
So let me draw this small differential volume dz. And this is 2b and this is w. Okay. So heat enters this plane by
Conduction.
conduction. Again, let me draw it. Heat leaves this plane by
Conduction as well.
conduction.
Yes.
What about this plane?
Convection, because it's exposed to the ambient temperature, so convection.
So heat leaves by this through this plane by convection.
Yes, sir.
What about this plane?
Convection.
Convection. What about this plane?
Convection.
What about this plane?
Convection.
Okay. So these planes, as we said, that this 2b is very thin. So 2b is almost a differential. 2dz also differential. So product of two different, almost differential. So it's actually very small in compared to others. So you neglect heat transfer through these green shaded planes. Heat transfer through other planes. So write a heat balance for this differential volume. And be ready to show it on the screen. So everyone agree with what he said? Varun Balkrishna, what he said. So if anyone has any question, any concern, please let me know. Okay. Varun, you can turn off your video now.
Yes, sir.
So why can't we take the differential element in the L direction?
Like this.
Yes, sir. Yes, sir.
You can take, but see, we will basically integrating in which way? So W is fixed. So variable, our problem here is that the length of the fin. So heat is flowing in Z direction, right? So a natural choice of differential element which will move in the direction of heat flow.
Okay, sir.
So, okay. Okay, so you get this as equation for temperature in the fin. Okay, any doubt on this equation?
So why we have not written that convection part of that dz into 2b?
Because that is very small in compared to other areas.
Okay.
The area, so this convection area, if you say here, so this area is dz times 2b, order of dz times b. And other areas are dz times L.
Yes, W.
So dz times W.
Yes.
Dz times W. So since W is much higher than B, so that is basically say W is 100 times B. So this convection will be 100 times less than others. So we neglected that.
Okay, sir.
All right. This is approximate, but it's worth doing that approximation. Okay, so now let us do a little bit of non-dimensionalization. First, we'll non-dimensionalize temperature. We call it theta. Theta equals to, we'll take as T minus TA divided by T wall minus TA. So, any idea why we do non-dimensionalization of an equation?
To remove the confusion between Kelvin and Celsius, etc.
Not exactly.
So to scale it to different dimensions, like for models to prototypes.
Okay. Anything else? Okay, so I think it will be clear if we just write this length dimension scaled. So we scaled length dimension is Z divided by L. So what is the range of values for L? What is the range of values for L?
0 to infinity.
0 to infinity. Well, actually, you do not know because different fin may have different L, right?
Yes, sir.
Some fin may have 3 centimeter L, some fin may have 5 centimeter L. No one stops a fin to be 5 meter L, or no one stops a fin to be 0.3 centimeter L. Okay. But what is the range of value for zeta? So if Z, actually Z varies from very large values. So numerical values for Z is anything. So what is the range of values for zeta?
0 to 1.
0 to 1.
Exactly. So that is the reason why we non-dimensionalize an equation. There are two reasons. First reason is that the values of non-dimensional variables should range between 0 to 1. So when you solve an equation, so most of the time or sometimes I should say, you do not have exact analytical solution of an equation. You need to do a various kind of approximations, order of magnitude estimate, and these things in engineering or in science in general. So for those kind of things, it's very, very beneficial to know what is the range of certain variables. So the primary purpose of non-dimensionalization is to bring the range of variables from 0 to 1. It's not always successful, as we'll see, but still non-dimensionalize helps to give a certain bound to the variable. For example, theta, T minus TA divided by TW minus TA. In the entire system, highest temperature is
TW.
TW. Lowest temperature is
TS.
T ambient.
T ambient. So T minus TA and TW minus T. T will be always between these two temperatures. So theta will be always between 0 to 1. So will be zeta. Okay. Another purpose of non-dimensional is that if you non-dimensionalize an equation, certain dimensionless groups come out. So that tells you which group of variable determine the nature of solution. For example, if you take Navier-Stokes equation and non-dimensionalize it, you will find that Reynolds number comes out. Okay, similarly, we'll see some variables coming out here. Okay, so now non-dimensionalize this equation, and before that, so we know that the equation itself doesn't tell the entire story, so we need a boundary condition. So what are the boundary conditions here?
At the like at Z is equal to 0, the T will be TW.
So at Z equals to 0, T equals to TW. This is the easier boundary condition. Much more ambiguous case will be at Z equals to L. So there are a variety of boundary conditions possible. And what is the most intuitive boundary condition?
T is equals to T ambient.
T is equal to TW.
T ambient. Yes, that is one of the boundary conditions, but that is for infinitely long fin. So there are actually 4 types of boundary conditions possible. So one of them, as you said, T equals to TA. That is basically infinite long fin. Another more physically relevant boundary condition, H times. So conductive heat flux at the fin tip is same as convective heat flux at the fin tip. This is called convective boundary condition. Another boundary condition is the adiabatic fin tip condition. So that we can say that is from fin tip there is no heat loss, as if fin tip is insulated. Now, which boundary condition we should use, that depends on what kind of fin we have and many other conditions. So since we are see the solution is available for all those conditions. So actually what you have to do is that you have to look at your situation and find out which boundary condition is more relevant for your case and use that. Since
Sir, can you repeat? Can you repeat what dou T by dou Z equal to 0? Which condition is it for?
That is called adiabatic fin tip.
Okay.
That means from fin tip there is no heat loss.
Okay. Yes.
Okay. So that is adiabatic fin tip boundary condition. So which condition is actually you have to use, that depends on the situation. And all those arises at different situations. And for time being, we'll take the simplest one, and that is the adiabatic fin tip. So for us, our condition will be that adiabatic fin tip at Z equals to L the gradient is 0. Oh, this is one dimensional dt dz equals to 0. Okay. Now non-dimensionalize this equation and boundary conditions, and tell me which dimensionless group you get.
Sir, here we have left out the MCP dt term, right?
It's a steady state. So heat in equals to heat out. So that is the heat balance for steady state.
Okay, sir.
Had it been unsteady state, we have to take d by dt of MCP dt. So you should be getting this by now. This is the dimensionless differential equation. And boundary condition at zeta equals to 0, theta equals to 1, okay. So this is our dimensionless group. Because everything in this equation is dimensionless, this has to be dimensionless. So you can check it, but you will find it to be dimensionless. And every dimensionless group is a ratio of two properties. Dimensionless groups always weigh two things. So which two things this is weighing?
Convective to conductive.
Convective to conductive what?
Heat transfer. Convective heat transfer to conductive heat
That is
transfer.
apparent from the expression in terms of physical quantity. This is actually, you can write it as, we denote it by n square. N square equals to HL square over BK. So we can write it as L square by B, L square by B 1 over K divided by 1 over H, right? So L square by B, some length dimension divided by thermal conductivity 1 over H. And what is the numerator? So if you see the conductive resistance, see when we add up all the resistances, we always have some L divided by K, right? So that is the conductive resistance. We have L divided by some length dimension divided by K, that's the conductive resistance. 1 by H is convective resistance. So this is a ratio of conductive to convective resistance. I don't know why it doesn't let me scroll down freely unless I put something here. Maybe some settings is there. Okay, so this is the ratio of this non-dimensionless group. N square is the ratio of conductive to convective resistance. Okay, so this is called Biot number. It's written as Biot number, but it's spelled as Biot number. I never heard people pronounce, at least in India, it as Biot number, but that is what Leonhard say in his book. So I go by that and I call it Biot number. Okay, so this is the conductive to convective resistance. All right, so now it's time to solve this equation. So now while solving, you know that why I put it as n square. So what is the solution of this equation?
It is similar to SHM, like SHM equation.
Yeah. So what is it? Just tell me, spell out the solution.
Some A times sine omega t.
Well, we write it an exponential. Okay. So it is d square minus n square equals to 0. So d square equals to plus minus n. So the solution is C1 e to the power n zeta plus C2 e to the power minus n zeta. Exponential solution. And we'll also need, because the boundary condition has d theta d zeta, so let us also write d theta over d zeta equals to C1 n e to the power n zeta minus C2 n e to the power minus n zeta. Now let us put the boundary conditions. So zeta equals to 0, theta equals to 1, that is 1 equals to C1 plus C2. And here we know that 0 equals to C1 n e to the power n minus C2 n e to the power minus n. So solve it and tell me what is C1 and C2.
Sir, can you please explain the second boundary layer condition, that adiabatic one?
Adiabatic fin tip. So some cases you can assume. So actually, if you say that no heat transfer occurs from the fin tip, you can take adiabatic fin tip condition. No heat transfer means no heat should go to the fin tip either. So you have dt dz equals to 0. Even if you have the infinitely long fin, so this condition will help for that as well.
Okay, sir.
Okay. So just substitute C1 equals to 1 minus C2. So 1 minus C2. So C2 we will get easily. C2 we will get as so 1 minus C2 e to the power n. C2 so n goes away. So C1 1 minus C2.
C1 will be e to the power minus n divided by e to the power n plus e to the power minus n.
Yeah. So C2, so e to the power n equals to C2 e to the power n minus e to the power minus n. C2 equals to?
So it will be 1 by 1 plus e to the power minus 2n.
Yeah. So e to the power n. Okay. So C1 will be to the power n. So I have written the solution in slightly different form. So probably that's also fine. So let me first make some space here for me to scroll down. Yeah, so C1 n is 0, C1 e to the power n minus C2 e to the power minus n. C1 equals to 1 minus C2 e to the power n minus C2 e to the power minus n. From here we get from here we get 0 equals to e to the power n. 0 equals to e to the power n minus C2 e to the power n minus e to the power minus n. C2 so I have written it as e to the power 2n. What's wrong here? Something is not matching with what I have here.
So it should be plus.
Denominator e to power n plus e to power minus n.
Oh, here plus, no?
Yes, sir, in the denominator.
Yes, sir. Now it's fine. So if I just multiply e to the power minus n, so this will be 1 divided by 1 plus e to the power minus twice n. Still I have something wrong here. Okay, so this is correct, no? C2?
Yes, sir.
It's not plus 2n, no?
Yes, sir, that's correct. Yeah.
Okay, okay, all right. So now C1 is 1 minus C2. C1 equals to 1 minus 1 by 1 plus e to the power minus 2n equals to 1 plus e to the power minus 2n minus 1 plus e to the power minus 2n. So this is C1 is e to the power minus 2n by 1 plus e to the power minus 2. All right. So this is now the solution is ready. Okay. So now we have to obtain what is the total amount of heat flux, right? So now remember, our purpose was to get Q actual, that is the total amount of heat that this fin was able to transfer. And how will you obtain that? Now the temperature profile is known. So using that temperature profile, so how will you obtain that in a Q actual?
Sir, heat loss is
Integrating over a differential
NCP/dt.
volume.
No, it's not dt. There's no time, so it's a steady state. It's a steady state situation.
Sir, K into A into dt by dz at z is equal to 0, and A will be W into 2B.
Yeah. So one of the ways you can think of this total heat transfer is that total convective heat transfer, because TA is known, T is known, convective heat transfer coefficient is known, but that will require an averaging over the entire field surface. So what I have heard in many classes before, not many, sometimes, is that take this surface and take this heat transfer from any differential area and then integrate it over the entire surface. That in principle can be done, but that is much more cumbersome than recognizing that. What happened? So it is easier to recognize that whatever heat that is pushed through the base.
Sorry to interrupt you, sir. Sir, are you sharing your screen?
Yes. So
Sir,
how
we
long
can't
it is
see
not
anything.
being shared?
It's not visible, sir.
Sir, just now when something happened.
Okay, isn't it visible now?
Yes, sir, it is visible.
Okay. Something happened here also. Suddenly this one note vanished. So just let me know if again it interrupt. Huh? So it is easier to understand and recognize that whatever heat is being pushed through the base at steady state, in all part of it has to be transferred. There is no other way. If you push something, if it's steady state, it has to be transferred. Otherwise, there will be accumulation. So the total amount of heat transferred, as said by someone, is that Q equals to L times twice B, that is the area. Now heat transfer, heat flux at the base. Okay, so that is the Q actual. And now we know that dTd is it. So first let us write it in terms of this non-dimensional variable. Well, I have divided it here, so I should have multiplied it. So TW minus TA. Okay, so 2B TW minus TA times L. Okay, L actually cancels here. This L cancels, times d theta d zeta, and zeta equals to 0. Okay, so this Q actually is okay. So L times 2B area times flux, that is clear. So now what I am doing is that I am transferring it in terms of the non-dimensional quantity. So maybe I can do it once again. This step. So this I have written as L times 2B is here. D, instead of T, I have written T minus TA by TW minus TA. So I divided by TW minus TA, so I have to multiply it by TW minus TA. And I have dz by L. I have to multiply here also 1 by L. All right, so now this step is clear. So LL cancels, this remains d theta dz. So now we have to put d theta dz at zeta equals to 0, which is now we can put it from here. So this is C1n minus C2n. So this is twice B okay. So this is twice B C1n is C2n is okay. So this is the Q actual in terms of unknown variables, and Q ideal or Q max equals to the width is what was that width, right? Width times L, that is again twice up and down surface, and the entire surface is at a temperature of TA, there's a TW minus TA. So this is the convective heat flux. This is the area through which convective heat flux is happening. All the side and tip areas have been neglected. So the efficiency is twice B TW minus TA, this function, divided by twice WL H TW minus TA. So this cancels, and we have these two cancels. So we have this thing in the numerator. Denominator we have LWH over B. Now LW H over B. Something I missed. Something I missed somewhere. This should come as n itself. N square or n, it should come as n square. You see that H L over B is here. Some key.
Sir, n should come. Sir, n should come. We can take common n from the Q actual.
Huh?
Sir, n should be with Bn, like
twice B.
Sir, in Q actual, I think K is missing.
K is missing, exactly. Q actual K is missing. Okay, so here
in Q actual, the area should be 2B into W, right? Because that is the area perpendicular to the direction of heat flux.
Yeah,
2B
2B times 2B times W, exactly. Q actual 2B times W. Yeah, that's what I'm wondering that. So this will be, instead of AL, it will be 2B times W, all right? So L will not cancel. So there will be, so here it will be W by L. So 2B W by L. So 2B W by L. All right. So beta equals to Q actual. So 2B W. So is L square here. W cancels. Okay. So it will be L square H by B. L and K. Here there will be K along with B. So there will be K. There will be K. There will be K. Twice KB. Twice KBW over L. Twice KBW over L. So twice KBW over L. So there will be n squares coming here, huh? Okay. So let me clean up this part. So is this correct? This is twice KBW over L, no? So eta equals to twice KBW over L, TW minus TA. Twice W L H TW over T. This cancels and this becomes, so 2W cancels. So it becomes this thing divided by L square H by K V. So L square H over KB is N square. So this becomes divided by n square. So n square, this n cancels, and you will find this to be so n cancels, it becomes e to the power minus 2n minus 1 divided by 1 plus e to the power minus 2n divided by n. So if we multiply it e to the power n, it will become e to the power n minus e to the power minus n divided by e to the power n plus e to the power minus n divided by n. And what is the numerator? So numerator looks like some hyperbolic function. So you're familiar with hyperbolic function, no?
Sir, I think it will be e to the power of minus n minus e to the power of n.
Yes, sir. With
That you can bring a minus sign here. So you are saying that you just bring a minus sign out, so you will get e to the power minus n minus e to the power n divided by e to the power minus n plus e to the power n.
It will be e to the power of minus n minus e to the power of n.
So I just bring a minus sign here out.
No, the minus sign won't be there in the second.
Okay, so you are saying that this is plus. So some sign I missed somewhere. Okay, all right. Yeah, this negative of k will be here, right? So this here, when I miss the k, I miss the negative of k here. So all right, so there is some sign issue, so that will be resolved if we just take this one here. So I think I missed a minus sign here also. So then this will be plus, right? So what is the final expression then? So what is this in terms of hyperbolic function?
Tan hyperbolic n.
Yeah. So if you look at hyperbolic function definition, you will find that this is a tan hyperbolic of n divided by n. So you see that for this simple case, this expression for efficiency is a simple expression, and it's a function of what we called n is a parameter. It's some kind of bio number. Why I'm calling it some kind? Because usual bio number, you don't have two length dimensions cancelling or something like that. You get a clear single length dimension. So that's why I'm saying that there's a slight variation of bio number, but it's still a bio number or BO number. So if someone gives you all these properties H, K, L, and B, you'll be able to find out n, and in this putting in this function, you'll be able to find out the Finn efficiency. So the Finn efficiency is a property or is a function of convective heat transfer coefficient, thermal conductivity, and the geometry. So H, K, geometry. So in this case, geometry is simple. Only L and B defines geometry. But for more complicated fins, for example, a fin may have varying area. So even if a rectangular fin may not have a constant area, so its area may be varying. So the cross section of the fin may look like this. So in that case, the geometry will be this dimension, this angle, how quickly it tapers, whether it tapers linearly or whether it tapers in a quadratic way. So all these geometric factors will define the fin efficiency. Okay. So now let us solve a problem. So which tutorial? I think tutorial 1 is done, right? So open tutorial 2 and problem number 1. First read the problem, devise a plan. So I'm reading the problem, just make sure that you can see the same, you are seeing the same problem. To increase the heat dissipation from a 3 centimeter OD pipe, circumferential fin made of aluminium was soldered to the outer surface. The fins are 0.1 centimeter thick and have an outer diameter of 6 centimeter. If the tube surface temperature is 100 degrees centigrade and the ambient temperature is 25 degrees centigrade and the heat transfer coefficient between the fin and the environment is 65 watt per meter square Kelvin, calculate the rate of heat loss from the fin. Simple problem. So all the geometry, etc., everything is given. So you need an expression for fin efficiency. So how will you get fin efficiency? So this is not a rectangular fin. So you need proper expression for that. So that we have to find out from textbook. Yeah, so I got a message that something went wrong. So am I audible and visible to you? My screen is also visible?
Yes, sir. Yes, sir.
Yeah, here it is. So this is the efficiency chart for the kind of fin we are looking at. You see that first I have to identify that this fin is not what kind of fin I am already derived. So please do not use the same tan hyperbolic n divided by n and n is some strange dimensions. So you have to find out the proper efficiency chart. See, this is efficiency chart for the kind of fin we are talking about. But this is a different geometry, so you have to use this chart and not this chart. So I don't know why people sometimes use the wrong chart. So you have to, is a picture is given in the chart. So as soon as I give in the exam, people start using, so use the same expression, tan hyperbolic n divided by n. So this is the chart that you are supposed to use. So use this chart and solve this problem and tell me what is the heat loss from the fin. So you see that this Biot number is slightly different here. Again, it's this conductive to convective resistance, but the dimensions you have to find out. What is the eta fin efficiency? Has anyone obtained the efficiency?
Sir, is it approximately 55%?
55?
55%.
Okay, so let me see how others are getting. So R1, okay, so this is 3 centimeter OD pipe and 6 centimeter outer diameter. So R2 is 3 centimeter. So R2 is 3 centimeter. T equals to 0.1 centimeter. T equals to 0.1 centimeter. R1 equals to R1 equals to 1.5 centimeter. Okay. R1, R2. L equals to R2 minus R1, that is 1.5 centimeter. So T by 2 equals to B equals to 0.05 centimeter. So R2C equals to R2 is 3 centimeter plus T by 2 is 0.05 centimeter equals to 3.05 centimeter. R2C. LC equals to L is 1.5 centimeter plus T by 2, that is again 0.05 equals to 1.55 centimeter. Okay, LC. AP equals to LC times T, 1.55 times 0.1 equals to 0.155. All right. So the geometric factor or Biot number comes to be, this is centimeter square. So LC to the power 3 by 2. So first we have to see that all the units for H and K. So H is given as H equals to 65 watt per meter square Kelvin. So length dimension has to be in meter. So and K equals to 200 watt per meter Kelvin. So everything else when it comes to be has to be in meter. So LC is now equals to 1.55 into 10 to the power minus 2 meter. AP equals to 0.155 into 10 to the power minus 4 meter square. So we can write it as LC cube H divided by K AP, the entire thing to the power half. So LC cube is 1.55 10 to the power minus 2. That is LC. Cube of that divided by 0.155 into 10 to the power minus 4. Okay, that comes to be 0.24 into H is 65 divided by 200 into 65 divided by 200. So 0.078 square root. Point 0.28. The geometric factor BO number comes to be 0.28. If it's 0.28, it will not come 0.56. 0.28 is somewhere here, and R2C over R, and R2C over R1. R2C equals to, R2C is 3.05 centimeter, 0.05 centimeter over R1 equals to 1.5 centimeter. So R2C over R1 is approximately 2. So we have to take the second curve from the top. And with this, if we go to 0.28, it will hit somewhere around above 90%. Okay. So say 92%, 95%, whatever you feel suitable. So let me write down the numbers that I'm getting. I just don't want to move from this one. So let me see if I can write here possibly. So here I'm getting, so first I want to make sure that you all get LC equals to my luck's not working. So make sure that you get these numbers. LC equals to 1.55 into 10 to the power minus 2 meter, and AP equals to 0.155 into 10 to the power minus 4 meter square. Then you get the geometric factor 0.28. So everyone getting these numbers?
Yes, sir.
Okay. So are you getting fin efficiency about 95% or above 90%? At least something close
From
to
that curve, yes, it is in between 80 to 100%. Because I got the BO number as 0.2794, roughly around 0.28.
0.29, that's fine. 0.28, you hit somewhere here, right?
Yes.
You hit somewhere here, and it's above 90, I think, because 90 is somewhere halfway. Okay, so don't worry about that much. So 90%. Let us take 90%. Huh? Okay.
Okay.
So anyone having any difficulty in reading this curve? So I think some mistake occurred because of the dimension. So dimension you cannot take in centimeter. So you have to take
Sir,
meter.
one doubt.
Huh.
Sir, in the question it is given initially that 3 centimeter OD pipe. So what is that OD?
OD is outer diameter.
Sir, after that also that outer diameter of the fin is given.
So see, you see that picture here. So this is outer diameter of the pipe, and this is the outer diameter of the fin.
Yes, sir, got it.
Okay, so efficiency, everyone report around 90%. If you don't get, you are not getting 90%, you just take all the geometric numbers. So maybe the unit mismatch is one of the reasons. Otherwise, it's a straightforward thing. Now tell me, what is the heat transfer to the fin?
Pi r1 square, pi r2 square minus r1 square into h into t minus t ambient.
You are talking about the area, no?
Yes, sir.
Yeah, pi rho square minus r square. So that will be your area of one side. And
yes,
you
sir,
have to
into
make
t.
it twice of that, because the left and right, both sides, you will get heat transfer. Neglect the tip area. So that is your area for heat transfer. What is the heat transfer rate?
$18.6.
Yeah. This will get something similar. 18, 19. Okay, everyone comfortable with this?
Sir,
Yes,
if
sir.
the fins are really close to each other, wouldn't the air between the fins also get heated up, and that would also reduce the efficiency of the fins?
No, normally the fins are that much close so that they don't affect each other. So even if they affect each other or not is not a question. Whether this H that you are using, whether that is getting lower or not. So normally fins are very close, so they don't affect the H. H remains high. So that's why most of the time the area of fin is much lower than base area. So you just get the heat transfer from each fin and multiply the number of fin, you get the total heat transfer. You don't even bother about the base. So fins are so closely placed in many cases. So you have seen the picture I have shown, the very closely placed fins. You can find those again in Leonhard. So the answer is that closely placed fins will not affect the heat transfer until they are jam packed. So not that much is done. So people know that how closely you can place without affecting heat transfer. Okay, so now let us move. So our last topic for steady state conduction is the conduction with heat generation. So many cases we have heat generation in the system. So can you give any example of the system where heat generate inside a solid?
Nuclear reactions.
Nuclear reaction, you have the rods, so this fuel rods. So inside the fuel rods, there are nuclear reaction occurs, the rods heats up, and you need to have certain way to remove that and use that heat. So that is one of the examples. Any other example? The high tension lines that you see that's running, so those are very, very hot. So any idea what is the temperature of those high tension lines? Any guess?
So 1000 degrees Celsius.
हाँ कितना?
1000 degrees Celsius.
हाँ?
1000 degrees Celsius.
Oh no. The birds sit on those, no. So actually those are 30, 40, 50 sometime depending on the location and other factors. This can sometimes go up to 100. Never beyond 100 I haven't heard. Actually, I was not aware of the temperature of those wires either. So I knew that those were heated up because the current is high. So I square RT heating is there. But recently I was contacted by a guy who was trying to sell or make some kind of paint which will increase the emissivity of those lines and reduce the temperature. I don't know the details of the problem yet, but he told that this goes up to 100 in certain cases, but 30-40 goes. I don't know whether I think I have seen birds to sit on those, but if it's 100 degree, of course, the birds cannot sit on those wires. So I square RT heating is one of those that happens, and those wires are not insulated. So special problem occurs to insulated wires. So because if the temperature goes too high because of high current, what will happen? The insulation may melt and even burn. So that is what is the reason for fire in many cases. So these are I square RT heating. So any other situation where you see the heat generated inside the volume?
Any sort of reaction vessel.
Huh?
Any sort of reaction vessel.
Any reaction vessel. Mostly reaction vessels have liquid inside. So a solid, but this answer is correct. The reaction gives heat. So not only nuclear reaction. So we have three examples. One is that I square RT heating. Another is atomic reactions or nuclear reactions. And another one is the normal chemical reactions. You see that the concrete, after their casting is done, you need to cure the concrete for some time. So actually an exothermic reaction occurs for the cement. Cement curing is an exothermic reaction. So actually heat is generated inside and that is transmitted to the outside and then finally to the ambient. So that's another example of heat generation. So we'll think of a case where this I square RT heating only. So but other cases are also identical. There's not too much difference. But for our ease of thinking, we'll think of I square RT heating. And we'll consider so let us see SE is our notation for heat generated per unit volume. So this is heat generated per unit volume. So why it changed notation from Q dot to AC? The reason is that we call it a source term. So heat source term. So that's the reason for this S. And this subscript E indicates that's the electrical reason. So the electrical heat source term SE. So that is typically used in many heat transfer textbooks. So that's why I retained that. And this is the rate. This is the per unit time. So rate of heat generation per unit volume defined as SE. So this is you know that if you have a conductor of resistance R and the current that is flowing through is I square R, that is the total amount of, that is the rate of heat generation for that particular resistor. And if A is the area of the resistor, L is the length, that is the volume of the resistor. So you can say this is the rate of heat generation per unit volume, I square R divided by AL. Okay. And you also know the resistance is proportional to length and inversely proportional to area, and the proportionality constant is called resistivity, rho. So we can replace R with this expression. So if we replace that, so we have I square rho L by A square L. So this cancels out. So now we denote I equals to I by A. So this is I square rho. So this is in terms of more often intensive properties. This resistivity, and I small I is called current density. So although electrical engineers call it current density, it's not per unit volume basis. This is basically current per unit area. This is basically I square by A square. So this is I small I square. So heat generation per unit volume is I square rho. Any question on our I square rho thing? Okay, so now let us write down a heat balance equation in cylindrical coordinate. Since our concern is electrical wire, which is carrying current, and we have an insulation surrounding. So the temperature in this phase will be called T. Temperature in this phase will be called Ti. And this is a cylindrical system. So first let us write down a heat balance for a general cylindrical cell. So let us just draw a differential shell, axis symmetric. This is the axis. This is R, and this much is dr. Okay, so length, we can take any length L. So I've written this heat balance. This is just same thing, just I'm repeating. So heat flux at R times area at R, that is 2 pi RL. So this much is heat in equals to heat in plus heat generated. Heat generated, so that is SE times volume. Volume is 2 pi R dRL. So heat entered, heat generated at steady state, that must be heat that is leaving. Well, so this entire thing is at R plus dL. So that means we can write it as, so 2 pi L I can cancel, 2 pi L, 2 pi L, 2 pi L cancels. So I can write it as dr bringing down here. So d by dr of R times QR. You see that R remains, equals to R times SE. So now we can write QR equals to minus K dt dr. So this becomes minus K times d by dr of this typical cylindrical coordinate thing. QR minus I have taken, so dt dr equals to R times AC. Okay, so this is our heat balance equation. So we can simplify it slightly. We can write it as d by dr of R dt dr equals to minus R SC over K. Okay, so the cylindrical coordinate heat balance with heat generation term. Any question on this one? So we are done for today, so we will not do anything more. So just make sure that this heat balance is clear to you. We'll pick up from here next week. Okay, so that's it for today. So just make sure that the last thing, that heat balance is clear to you. And if you don't have question, if you have question, you feel free to ask. If you don't have question, feel free to leave.
Thank you, sir.
Sir, I did not understand that if the fins are very closely spaced, then the temperature between them, how can it be ambient temperature? It will be higher than that. So, and if it's higher, then the heat transfer rate by convection should also be lower. So, I didn't understand how we can consider the temperature between two very closely spaced fins to be equal to T ambient, as that is the temperature at infinity, right? So it's like very
What is
fast.
the, so you are now, I think I understand that you are learning boundary layer theory in convection, right?
Yes, sir.
What is the thickness of boundary layer?
Sir, I don't remember the formula, but it's where the temperature gradient is 0.99 of the maximum.
No, that's fine. That's the definition of the outer skin of boundary layer. The typical thickness of a boundary layer is about a millimeter or two. So if you keep two fins 4 millimeter, 5 millimeter away, half a centimeter away, then the boundary layer will not even be thicker than half of those. So the question is that how close is close? If two boundary layers do not touch each other, that is close. That is far enough. So are you able to see the screen here?
Yes, sir.
Okay. See these two fins, say this is one fin, this is another fin. Okay. And beyond the boundary layer, temperature is T ambient. And this is how the boundary layer thickness grows. Okay. These are the two adjacent fins. So here it is T ambient. So provided this gap is greater than twice into thickness of boundary layer. You agree to that?
Yes, sir. Yes, sir. I got it.
Yeah. So normally these thicknesses are very small. So this is for a fin of 6 centimeter. This thickness will be something around say 1 millimeter, 2 millimeter. So if you are placing them 4 millimeter apart, that should be fine. Normally people do not place them closer than that.
Okay, sir. Thank you, sir.